Perhaps you have looked up at the night sky and wondered how it all began, how something could rise from nothing, how stars, light, and even we ourselves came to exist. Questions like these rarely have simple answers, yet their mystery has a way of keeping us listening. Tonight, we are going back to that beginning. Not forward, but backward, beyond every atom and every beam of light, to a moment before anything existed at all. 13.8 billion years ago, everything began. One moment, there was nothing. The next, there was everything. And you can't help but ask, how? It's maybe the biggest question in all of science, the one that refuses to stay still, sitting somewhere between physics and philosophy, between math and mystery. Stephen Hawking wondered that too. He once said maybe there really was nothing before. Not even before in the sense we understand, because before time, there was no time. If the universe carries both space and time within it, then its beginning wasn't just the start of things, it was the start of when. Before that, there was no before. Imagine rewinding the fabric of space and time itself, watching it shrink and curve until it loops back on itself, smooth and complete. Trying to look beyond that point would be like asking what lies north of the North Pole. It sounds clever, but it doesn't make sense. Or maybe there was no beginning at all, just the edge of what we can see, the limit of our observation. We know something happened, something fast, a fraction of a second where the universe expanded at impossible speed. We call it inflation. That's what put the bang in the Big Bang, the moment that made everything possible. Some physicists think so, that our universe is just one bubble in an endless foam, new universes forming, expanding, separating forever. A multiverse, or maybe instead of one explosion, there's a rhythm, an eternal heartbeat of creation and collapse. The big bounce, in that picture, everything expands, slows, contracts, and then begins again. No first moment, no last, just an infinite pulse. Paul Steinhardt believes that could be true, that we're living in one cycle among countless others. Roger Penrose thinks time and size lose meaning at both extremes, the infinitely small and the infinitely vast. When everything is beyond measure, maybe it all becomes the same. Like a game of chess played on a board the size of a pocket or a planet, the rules don't change, only our perspective does. Or maybe the truth lies somewhere stranger still. Maybe our universe was born from the collision of higher dimensions, two vast membranes in an 11-dimensional space, brushing together for an instant, igniting everything we know. Superstring theory calls them brains, and our entire cosmos could just be one of them, rippling in that hidden space. And yet, even with all that, we might still be missing something, some corner of mathematics or physics, left in shadow, waiting to be seen. For now, the origin of the universe remains a mystery, a question with too many right answers. But one thing is certain, 13.8 billion years ago, it began. The cosmos opened its eyes, and everything since has been its story. And the story it began is vast beyond measure. Even if we flew toward it at 50,000 kilometers an hour, it would take over 80,000 years to arrive. 80,000 years. And that's just the closest one. The Milky Way holds 100,000 million more. Think about that for a second, and then try to imagine the rest. Because speaking of heat, have you ever wondered where the hottest place in the universe really is? You'd think it would be the core of a star, right? A natural fusion reactor burning itself into brilliance. 15 million degrees Celsius, give or take. Sounds extreme, but it's not enough. Not yet. What about a supernova then? A star's final scream, tearing itself apart, hurling fire across light years. Temperatures there reach 100 billion degrees. 100 billion. But even that isn't the limit. The record, strangely enough, was made here, not out there, under the snow in Switzerland near Lake Leman. Beneath the ground, inside CERN's Large Hadron Collider, two lead atoms collided in 2012, and for a fraction of a second, just a whisper of time, the temperature hit 5.5 trillion degrees Celsius, 50 times hotter than a supernova, but still not the hottest possible. So what does temperature really mean then? It's not just heat, it's motion, it's energy, It's how fast things shake, vibrate, move. At absolute zero, minus 273.15 Celsius, motion stops, at least in theory. Everything frozen, perfectly still. But go the other way, and there's a limit too. At absolute hot, where motion becomes destruction, where particles tear themselves apart. That limit, that wall of fire, is called the Planck temperature, 1.4 times 10 to the 32 Kelvin. Beyond that, even physics starts to unravel. Max Planck, a quiet German physicist from the early 20th century, gave us that number. He was trying to understand light, tiny packets of it, photons, but his equations led deeper. Using the constants of nature, light speed, gravity, his own Planck constant, he defined scales so small we can barely imagine them. The Planck length, 1.6 times 10 to the minus 35 meters, 100 quintillion times smaller than a proton. The Planck time, the time it takes light to cross that length, 5.39 times 10 to the minus 44 seconds. And the Planck temperature, the point where radiation's wavelength shrinks to that same tiny scale. You can't go smaller, you can't go hotter. Our brains, our senses, they're built for mountains and oceans, not numbers like these. But still, there's something about them that matters. Because at the very beginning of everything, when the universe was nothing but a flash, a fraction of a second old, those scales ruled. Planck time, Planck length, Planck temperature, all of it. The physics of creation itself. And thinking about that, about how everything we know came from that impossible heat, that instant of pure energy. It's almost too much. But also, it's beautiful, isn't it? Right. So the thing about our universe is that it's expanding. It has been always becoming less dense, thinner in a way, as space itself stretches. Because you'd think something that expands must have started small, a point maybe, but that's not necessarily true. Some scientists say if the universe is infinite now, then it's always been infinite. No edges, no outer wall. It didn't grow from a single dot into something huge. It just became less dense, more spread out, like paint fading across a canvas that never ends. But our observable universe, the part we can actually see, that's different. It's not the whole thing. It's just the region from which light has had time to reach us. Everything beyond that, well, it's invisible to us, forever out of reach, because light hasn't had the time to get here yet. 13.8 billion years, that's the limit. That's how far light has traveled since the beginning. And the farther back we look, the smaller that bubble gets. Until, at the very start, all of it, everything we could ever see, was packed into something unimaginably tiny. A space, 1 Planck length across, 1 Planck time old. The temperature then, the Planck temperature. Beyond heat, beyond fire. And that moment, that impossible fraction of a second after time itself began, is called the Planck era. And it was weird. Really weird. Because today, the universe runs on rules. Laws of nature, forces that keep things together or push them apart. The strong force, the weak force, electromagnetism, and gravity. 4 players shaping everything. The first 3 we can quantize. That means we can describe them as little packets of interaction, messengers. Gluons for the strong force, W and Z bosons for the weak, photons for the electromagnetic. They behave like particles. Tiny parcels of energy. But gravity? Gravity refuses to fit. Einstein showed us why. He said it's not a force in the traditional sense. It's geometry. The bending of space-time itself, the shape of reality. And we've tested that. We've seen stars curve light. We've watched clocks slow down near massive objects. It works. It's beautiful. But go back to the Planck era and everything falls apart. Because then the entire observable universe was smaller than a proton. Too small for Einstein's equations. General relativity stops helping there. Quantum mechanics takes over. And quantum rules are different. They're messy, probabilistic. Nothing is certain. A particle isn't anywhere until you measure it, and even that changes it. The act of looking alters what's real. And that's fine for atoms or electrons, but not for the universe itself. The problem is, those two frameworks don't agree. They describe opposite sides of reality. One for the vast, the other for the tiny. And at the Planck scale, they collide. So we're left with questions. What does gravity look like when everything is quantum? What does space look like when it can't even decide where it is? We don't know, not yet. But that moment, the Planck era, holds the secret. The birth of everything. The instant when the universe tried to obey two masters at once and broke the rules of both. So researchers are still looking for it, right? This missing piece, this thing called quantum gravity. It's supposed to tie together the two giants of modern physics, relativity and quantum mechanics, to finally explain what really happened in the first instant after the Big Bang, in that impossible flicker of time we call the Planck era. But here's the problem, and it's a big one. We can't test it, not directly. The energies needed are, well, absurd. To study gravity on that scale, you'd need a particle accelerator the size of the solar system. Imagine that, an instrument stretching from the sun to Pluto just to peek at the way gravity worked at the beginning of everything. So we turn to theory, because math can go where machines can't. One idea says maybe gravity, like all the other forces, has a messenger, a particle called the graviton. Tiny, elusive, almost ghost-like. But gravity is weak, ridiculously weak, so its messenger would be nearly impossible to catch. Another idea, called loop quantum gravity, takes a different path. It imagines that space itself isn't smooth at all, but made of tiny loops, woven like a fabric, too fine to see. And if you rewrite Einstein's equations using those loops instead of continuous lines, the chaos of quantum gravity starts to make a kind of sense. Then there's string theory, maybe the loudest voice in the debate. It says everything, every particle is not a point but a vibrating string. The note a string plays, it's vibration. That's what makes an electron or a photon or even gravity. But there's a catch. The math only works if the universe has more dimensions, 10 or maybe 11, most of them curled up inside themselves, hidden from us like tiny rooms folded within reality. They call some of those structures brains, sheets of higher dimensional space that might be the foundation of an even deeper theory, something people just call M. Each of these theories feels both brilliant and impossible, elegant and absurd. They live in equations more than in images. But that's what we're trying to do, to picture what can't really be pictured, to imagine the universe before the universe as we know it existed. Back in the 1950 seconds, John Archibald Wheeler, an American physicist, gave that chaos a name. He called it quantum foam. He imagined space and time then as a seething, bubbling mess of energy where nothing stayed still for even a fraction of a moment. And at that scale, Heisenberg's uncertainty principle rules everything. You can't know position or energy or time with any clarity. So space-time, smooth and continuous today, becomes jittery and rough, a kind of froth where tiny wormholes and micro black holes appear and vanish like sparks. No cause, no effect, just wild fluctuation. For a heartbeat of cosmic time, anything could happen. And then, almost instantly, it didn't. After 100 million trillion trillionths of a second, the foam began to settle. The universe expanded, cooled, and with that, order began. The storm ended. The first quiet of creation began. So, here's something I keep thinking about. The universe we see today, it's not going to look like this forever. Not even close. But from here on, our theories, the ones we've built so far, they at least have a shot at describing what's coming. Because everything around us is ruled by four forces, four invisible hands shaping all of existence. Gravity, electromagnetism, the strong force, the weak force. That's it, just four. And somehow they control everything you've ever seen or touched. Imagine this. You sit down, turn on your TV. Gravity keeps you there. It holds you to the chair, holds the atmosphere to the planet, holds the planet to the Sunday. It's the reason you're not drifting away right now. But here's the weird thing. Gravity's weak, ridiculously weak. You can beat it with your arm just by lifting a remote. You press a button and something invisible happens. Infrared light, electromagnetic radiation, shoots across the room, hits the TV, and suddenly there's color, movement, stories, all made of light, visible light. Same family as that beam from the remote, just different wavelengths. That light travels into your eyes. And your eyes, they're not just lenses, they're miracles of physics and biology woven together. But underneath all of it are atoms, tiny worlds held together by the electromagnetic force. Electrons bound to nuclei by invisible attraction. And the nuclei themselves, they're held by something even stronger, the strong nuclear force. It binds protons and neutrons in the heart of the atom. And inside those, there's more quarks. 3 of them bound again by that same strong pull. You, your chair, your thoughts, everything held together by this cosmic glue. And as your eyes focus, as your neurons fire 200 times a second, by the way, that too is physics. Those electrical signals depend on potassium, an element made of atoms built from the same forces. But potassium has a secret. It's slightly radioactive. Right now, about 5,000 of its atoms inside you are decaying every second, quietly, invisibly. That decay, that transformation, happens because of the weak nuclear force. Weak, but essential. And out there, 150 million kilometers away, the sun is burning. Hydrogen turning into helium, fusion powered by the same forces. That fire gives you daylight, warmth, the chemistry of life itself. Without it, no Earth, no oceans, no you. And that reaction, again, the weak force at work. It may be called weak, but it shapes the universe. Each of these 4 forces, they're the framework of everything that exists. They build the cosmos. They build you. And yet, it wasn't always like this. In the beginning, just after time began, things were different. There weren't 4 forces, there were 2. How? That sounds impossible, right? But imagine flipping a coin, heads or tails, 2 equal outcomes waiting to be decided. In those first fractions of a second, the universe tossed that coin and symmetry broke. The forces we know today, gravity, the strong, the weak, the electromagnetic, all unfolded from that single moment of imbalance. A cosmic choice made before there was even space to fall through. Strange, isn't it? That everything you know, every motion, every heartbeat began with a coin toss. You know that moment right before a coin lands, when it's still spinning, still undecided, still full of motion? Before it settles, it isn't heads or tails. It's both. It's neither. It's just energy, all blur and possibility. You can't even see its faces anymore. Just a single flashing disk, spinning through the air, carrying every outcome at once. That's kind of what the universe was like in its earliest moments. When we look at the fundamental forces at extremely high energies, the energies that existed right after the beginning, something similar happens. The separate forces we know, they start to lose their identity. You turn up the temperature higher and higher, and suddenly their boundaries blur. You don't see 2 forces anymore. You see one, a single unified thing. Scientists call it the electroweak force. It's like the spinning coin again. Heads and tails now indistinguishable. And if you go further, push the energy even higher, the strong force begins to join in too. The idea is that at unimaginable temperatures, all 3 merge into one grand unified force. They call it the electro-strong force. It's neat, elegant, almost poetic, but has it been proven? Not yet. Even with all our particle accelerators, all the collisions we've created, we've only glimpsed the point where electromagnetism and the weak force come together. To see the strong force dissolve into that same unity would take energies millions of times greater than anything we can produce. Not even the fiercest events in the cosmos. Supernovas, black hole jets come close, they're still too gentle. So what about gravity, that final piece? Does it ever join the dance? That's the mystery of the Planck era, a time so early, so dense, that our current physics just breaks down. We can write equations, imagine scenarios, but we can't yet see them. Still, the grand unification theory remains one of our best ideas for how the universe behaved just after that era ended. For a moment lasting only a fraction of a second, the universe expanded and cooled, 10 million times longer than the Planck era. And yet, by the end of it, everything was still smaller than a single quark. Imagine that. All the energy, all the matter, the whole cosmos packed into something smaller than the tiniest particle we know. The temperature, around 100,000 trillion Kelvin, a trillion times hotter than anything we've achieved on Earth. In that state, the universe was ruled by the electrostrong force, a kind of chaotic unity where everything could become everything else. Photons blinked into existence, then into matter and antimatter, quarks and leptons appearing and disappearing almost instantly. Particles change form constantly, quarks becoming leptons, matter into antimatter, back and forth, an endless flicker of transformation. It wasn't order yet, it was potential. A cosmic storm of identity, where nothing stayed itself for long. And somewhere in that chaos, from that blur of energy and symmetry, the seeds of the universe we live in were born. Isn't that something? So, here's the thing. For a trillionth of a second after it all began, everything was chaos. Then suddenly something changed. Temperatures fell just enough to about 1,000 trillion degrees, which sounds absurd, right? But in that instant, the strong force broke free, two forces became three, and everything shifted again. But there's a problem with this picture, or maybe not a problem exactly, more like a puzzle. The equations work beautifully for those first tiny fractions of a second. They tell us how particles behaved, how the universe expanded, but they don't quite explain the universe we see now. When you compare the start to what we have today, something doesn't add up. It's like the Big Bang, our grand story, has a missing page. By July 2022, the James Webb Space Telescope was already out there orbiting the sun, 1.5 million kilometers from Earth, a golden eye staring back in time. After months of careful unfolding, calibration, and suspense, it was ready. And when it finally looked out, when those 18 mirrors focused on the oldest light, the results were shocking. American astrophysicist Alison Kirkpatrick saw the first images and later wrote that she lay awake at 3 a.m. wondering if everything she had done was wrong. And who wouldn't? The telescope was looking so far that every image was also a look back in time light from just 200 million years after the beginning. And in that early darkness, there were galaxies, real galaxies, already structured, organized, elegant, far too early by our models. How could that be? Theories of star and galaxy formation didn't predict that. They couldn't. That's what kept Kirkpatrick awake. But then, as often happens, the story got twisted. Headlines shouted that the Big Bang was wrong, that Webb had disproved it, but that wasn't true. Kirkpatrick never said the cosmos itself was broken. She was questioning our models of how galaxies formed, not how everything began. The mystery wasn't that the universe was false, but that we were missing a piece of the puzzle, a detail that might change the picture, not erase it. A storm in a cosmic teacup, you could say. So, yes, the Big Bang still stands, for now at least. But the truth is, it's been under deeper threat for a long time. When we look at the universe as it is today, huge and structured and strangely even, there are still things that don't quite fit, like the temperature. You'd expect chaos, extremes, hot here, cold there, but it's not. It's almost perfectly balanced, 2.7 Kelvin everywhere, across 93 billion light years of space, the same faint glow. How can that be? If the universe has been expanding for nearly 14 billion years, then 2 points that far apart should never have had time to even each other out. Light can only move so fast, right? So how did every corner of the cosmos agree on one temperature? The only way that could happen is if somehow the universe began already smooth, already in sync, already uniform. And that's the strange part, because quantum mechanics tells us the early universe should have been messy, full of fluctuations. So why wasn't it? That's the question. That's the mystery. And maybe, just maybe, that's where the next revelation waits. You know, there's this thing in cosmology, it's called the homogeneity problem, or, sometimes the horizon problem. Sounds technical, right? But it's basically asking a simple question. Why does the universe look so even? It shouldn't. Not if we think about how far light can travel and how little time it's had to do so. And then there's something else. Einstein's general theory of relativity. You've probably heard of it. It describes how mass and energy bend space and time, how everything that exists leaves its fingerprint on the fabric of the universe. Stars do it, galaxies do it, even black holes. They pinch and twist that fabric. Space-time itself ripples under their weight. But when you zoom out, when you pull back far enough, something strange happens. Those little ripples, those dents and curves, they seem to smooth out. The universe, on the largest scales, looks calm, flat even. And that's weird, because if there's enough matter in the cosmos, space should curve in on itself. It should be positively curved, like the surface of a sphere. You go far enough in one direction and come back to where you started. And if that's true, gravity should one day stop the expansion of the universe, pull everything back, collapse it all in a final echo of creation, the Big Crunch. But what if the opposite is true? What if there's not enough matter to pull things back? Then space wouldn't close in, it would open out, negative curvature, like the shape of a saddle, a geometry that stretches forever. And in that version, gravity never wins. Expansion goes on without end. Eternity written into the equations. So which one is it? What shape does our universe really have? That's the question astronomers keep trying to answer. They measure the background radiation, map the galaxies, check the angles, and strangely, almost impossibly, it looks flat, completely flat. And that's the part that makes everyone stop and think. Because the odds of that happening by chance are tiny, ridiculously tiny, like flipping a coin and having it land perfectly on its edge. So we call it the flatness problem. Another cosmic riddle. And there's still one more. Something missing. Magnetic monopoles, they should exist, at least according to theory. In electricity, you can have a single positive charge or a single negative charge, an isolated proton or electron, but magnets, they always come in pairs, north and south bound together. Break a magnet in half and you don't get one pole, you get two smaller magnets, each with their own north and south. No matter how deep you go, the pairing never breaks. And yet, in the early universe, we'd expect monopoles to form, lone magnetic poles wandering through space. But we've never seen one, not a single one. So what happened? Where did they go? In December 1979, a physicist named Alan Guth was thinking about exactly that. The missing monopoles, the strange flatness, the smoothness of everything. And suddenly he saw it. A single idea that could solve all three at once. What if the universe didn't expand slowly over billions of years, but exploded outward in an instant? Not chaos, not destruction, but inflation. A flash of expansion faster than the speed of light, stretching space itself from something microscopic to something vast. In a fraction of a second, everything smooths out. Every curve flattens. Every monopole spreads so thin, it's practically gone. And then, as suddenly as it began, inflation slows, and the universe continues its gentler, steady growth. The galaxies, the stars, everything we see today unfolding from that first impossible breath. It's wild, isn't it? That everything, even the problems, might come down to one single, breathtaking burst of expansion. You know, I've been thinking about that moment right after the beginning, the one Alan Guth talked about, the inflationary period. The universe doubling in size again and again, about 90 times, all in less than a trillionth of a second. 90 times. It's hard to picture. Exponential growth always is. Because when things double, they don't just grow, they explode. Think about folding a huge piece of paper. Just a sheet, nothing fancy. Fold it once, it's twice as thick. Fold it again, 4 times. Again, 8. But then it starts to get strange. After 7 folds, it's already as thick as a notebook. After 10, as thick as your hand. And that's it. That's where we usually stop. Because in the real world, the record is 12 folds. A girl in California did it back in 2002 with a sheet more than a kilometer long, ending with a stack half a meter thick. Half a meter! But imagine if we could keep folding, no limits, just thought experiment. 23 folds, a kilometer thick, 30, you're out of the atmosphere about 100 kilometers up. 42 folds, you're touching the moon. 51, the Sunday, keep going, and at 81 folds, you reach Andromeda itself, 140,000 light years wide. And 90 folds, that's beyond imagination. A single sheet thicker than the Virgo supercluster, more than 100 million light years across. That, Guth said, is what happened to the universe. The whole cosmos, one moment small and dense, the next an incomprehensible expansion. Not over years, not over seconds, but less than a trillionth of one. The universe didn't grow, it detonated into existence. It's what truly put the bang in the Big Bang. And here's the strange part. This violent growth didn't destroy order, it created it. The hot, dense universe suddenly became vast, smooth, almost empty. And somehow that solved problems that had haunted physicists for decades. The horizon problem, the flatness problem, the missing monopoles, inflation explained them all. It's elegant, isn't it? Because maybe the universe we see isn't all there is. Maybe it's just a bubble, an observable patch, limited by light's travel and time's reach, surrounded by more that we can never see. Our bubble stretches about 93 billion light years across enormous and yet just a fragment. And out there beyond our cosmic horizon lie the answers to those puzzles. The horizon problem, it's only a problem if you assume the whole universe is like what we can see. But if inflation stretched a once compact, thermally balanced cosmos far beyond our view, then our local region is just one small, uniform patch of a much wilder whole. The flatness problem, same logic. The universe looks flat to us, but that might be perspective. Stand on a beach and the ocean looks level, but rise high enough and the curve appears. We just can't rise high enough to see the cosmic curve. The wider universe could be curved positively, negatively, maybe even twisted in ways we can't imagine. And those missing magnetic monopoles, they're only missing if we think we're seeing everything. But maybe they're simply out there, far beyond our reach, hidden in the parts of the universe still beyond our cosmic shore. The biggest answers might lie forever, just out of sight, waiting beyond the limits of what light can show. You know, there's this idea that's always fascinated me, that in the earliest moments of the universe, there might have been magnetic monopoles, single poles of magnetism, like north without south, little fragments of symmetry that somehow survived the Big Bang. But if they really existed in the quantities our equations predict, where are they now? Shouldn't we have found one by now? Maybe not, because inflation, that sudden burst of exponential expansion, would have blown them apart, flinging them so far from one another that there might be only one in the entire observable universe. One, across a sphere 93 billion light years wide. So maybe it's not surprising we haven't seen it yet. Inflation, that word again, it's not just a theory anymore. It's part of our understanding, something so strange yet so consistent, that cosmologists have spent 40 years trying to uncover how a universe could suddenly, violently become vast. What triggered it? The timing seems to line up with something else, something deeper, the moment the fundamental forces of nature split apart. The great unification ended, And out of that fracture came the strong nuclear force. Some physicists think that when the X boson, this messenger of the old electrostrong force, decayed, it released a new field, a new particle, the inflaton, and that this field flooded the universe with energy, enough energy to make space itself explode. Imagine that. Empty space becoming its own engine, stretching faster than light, pulling apart quantum wrinkles until they became vast structures. Tiny quantum fluctuations blown up into the scaffolding of galaxies, of clusters, of superclusters, the seeds of everything that would ever exist. And all that stretching, that sudden expansion, cooled the universe by a factor of 100,000, thinning it, quieting it, emptying it out. But why did it stop? That's the question that still haunts physics. Why did the inflaton fade? No one knows yet. Maybe it decayed. Maybe it poured its energy back into the newborn cosmos in a phase we now call reheating. And that moment, that return of energy, that's when matter as we know it began. The universe was still unimaginably hot, but at last it was spacious, a little calmer, ready for structure. We call this the electroweak epoch, lasting till about a trillionth of a second after the Big Bang. A trillionth. There were quarks, leptons, matter, antimatter, all swirling in a storm ruled by three forces: gravity, the strong nuclear force, and the electroweak force, which was still a single hybrid thing back then. The energies were so extreme that the strong force barely mattered. The particles were wild, too fast to be bound, and the electroweak force couldn't quite hold them either. And gravity, though present, was missing something vital: mass. Without mass, it couldn't really pull anything together. So these newborn particles, they existed, yes, but they were unruly, untamed. They needed something more. Another drop in energy, another cosmic transformation. Only then would the universe begin to look like the one we recognize. It's strange, isn't it, how everything comes back to symmetry. Nature seems obsessed with it. Everywhere we look, in snowflakes, in shells, in the patterns of life itself, there's balance, repetition, order. The universe began in perfect symmetry, and ever since has been breaking it piece by piece, creating the asymmetries that made everything possible, including us. You know, I've been thinking about something strange lately. Why are we built the way we are? I mean, have you ever noticed how your body is mirrored, split neatly down the middle? 2 eyes, 2 hands, 2 lungs. We call that bilateral symmetry, and apparently we find it beautiful. Perfect symmetry is something our brains seem wired to love. But we're not the only ones, right? From the biggest whale to the smallest worm, life repeats this pattern. And when it's not twofold, it's something else entirely. Think of a starfish or a sea urchin. 5 arms, 5 points, radiating out like spokes on a wheel. That's radial symmetry. And what's wild is that you can find both these kinds of symmetry everywhere, in plants, in fungi, even in bacteria. It's like nature keeps reusing the same blueprint. But why? Scientists think evolution just prefers it that way. Balance forms are easier to build, easier to repeat. You don't need complicated instructions to make a mirror. Simplicity, it turns out, is powerful. And that's not just a biological thing. It's mathematical, it's algorithmic. The same kind of symmetry that shapes living things also shows up in the non-living world, in crystals, in snowflakes, in the laws of physics themselves. And that's where it gets really strange, because in science, symmetry means more than just something looking even or balanced. It means something deeper. It means something doesn't change no matter what happens to it. Like flip it, spin it, move it through space or time, and it still obeys the same rules. The laws of nature are symmetrical. Gravity, electromagnetism, the conservation of energy, all of it built on that balance. Positive and negative, clockwise and counterclockwise. the pull of gravity here, or in another solar system, exactly the same. The universe itself is symmetrical, or at least it almost is, because just like our own bodies, it's not perfect. When you look closer, your heart's not right in the middle. Your liver's off to one side. The cosmos, too, has little flaws in its balance. Some particles spin only one way, some never spin the other. There's more matter than antimatter, which shouldn't have happened. Electric fields and magnetic fields, so alike, and yet not interchangeable. Those tiny imperfections, those breaks in symmetry, they're not mistakes. They're the reason we exist, but it didn't start that way. No, in the first trillionth of a second after the Big Bang, physicists believe everything was in perfect harmony. The forces were one, the universe was balanced, and then it broke. The symmetry shattered as the universe cooled, like ice forming from water. Each drop in temperature split one force into two, each split birthing complexity, difference, structure. That's when mass appeared. That's when the universe became uneven, and in that unevenness, things could begin to form. It's called a phase transition, the same way vapor becomes water, and water becomes ice. The young universe went through its own phase changes, each one reducing its symmetry, each one making it a little less perfect and a little more interesting. Eventually, the four fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, crystallized out, distinct and separate. That's when matter as we know it began, the quark era, the first time the universe could build something, anything. It's wild to think that from that broken symmetry came everything, from atoms to galaxies to us. And speaking of scale, consider this. The biggest single object we found is a Hypergean star called UY Scuti. It's enormous, about 1,700 times wider than our sun day. If you dropped it into the middle of our solar system, it would reach past Jupiter's orbit. And yet, like every star, it's made of the smallest things. Hydrogen, helium, the lightest elements in the universe. Hydrogen itself, the simplest atom there is. For centuries, we thought atoms were unsplittable. That's what the name means in Greek. But of course, we were wrong. We learned to split them to see inside, and what we found changed everything. Inside an atom are protons, neutrons, electrons, tiny pieces of something even smaller. The discovery gave us energy, it gave us weapons, it gave us the key to understanding creation itself, and now we know even those particles aren't the end of the story. They're made of quarks, maybe strings, maybe something we haven't seen yet. So symmetry breaks and new things appear. Each layer reveals another, and maybe, just maybe, that's what the universe is really doing. Hiding perfection behind imperfection, balance behind chaos, waiting for us to notice. So, here's something that's been on my mind. You know how we think of atoms as the smallest bits of matter, tiny and indivisible? Well, they're not. Inside atoms, there are protons and neutrons. And inside those even smaller things, quarks, little entities, so strange that the deeper you look, the more it feels like reality is built from questions instead of answers. These quarks, along with electrons, they decide everything the way matter behaves, the way stars shine, even the shape of the largest star we've ever found, a giant called UY Scuti. But wait, how do we know that? How do we even see something so small that it's beyond all sense of scale? The answer, oddly enough, is by breaking things. For 200 years, physicists have been smashing particles apart, trying to see what lies within. And the only way to do that is to give them energy by hurling them close to the speed of light and letting them collide. What comes out of those collisions is chaos, wreckage, debris. But inside that chaos, there are clues, fragments that fit together into a picture. That picture is what we call the standard model. It's our best attempt to describe everything we see, from galaxies to dust. So far, it works. Ordinary matter, what we're made of, is mostly protons and neutrons together, called hadrons. But here's the twist. Those hadrons aren't fundamental. They're made of quarks, each one with its own properties, mass, charge, spin, and something physicists decided to call color, though it has nothing to do with color as we know it. Why color, then? Because it helps explain how they bind together, how the invisible glue holds the universe in place. A proton, for example, is 2 up quarks and 1 down. A neutron, 2 downs and 1 up. Simple, right? But then it gets weird. There are more kinds, flavors. They call them with names that sound like a joke. Strange, charm, top, bottom, exotic, fleeting, unstable. They exist for a moment and then vanish, glimpsed only in the briefest flashes inside colliders. And when we break hadrons open, looking for something smaller than quarks, we find nothing. Nothing smaller. No substructure. It's the bottom of the rabbit hole, at least for now. And electrons, same story. They seem to be fundamental too. A different family of particles called leptons. The ordinary ones, the ones orbiting atoms, are negative. But their cousins, they show up too, ghosts from the quantum sea. So the standard model, the grand summary of all this, it says there are 12 building blocks of matter, 6 quarks, 6 leptons, plus their antimatter twins and the force carriers, the messengers that make the universe stick together. Photons for light, gluons for the strong force, W and Z bosons for the weak one, and gravity, maybe it has a messenger too, a particle we call the graviton. But if it exists, it's hiding. Still, with these, we can explain nearly everything. Almost. Because there's one missing piece. Mass. Every element in the universe, from hydrogen to plutonium, has its own weight, its own heft. Most of that comes from protons and neutrons in the nucleus. But here's where it turns strange again. If you weigh a proton, it's heavier than the sum of its parts. Much heavier. Why? The quarks inside account for only about 9% of its total mass. The rest, the other 91, comes from pure energy trapped inside. From motion, from fields, from the strange dance of gluons, tying everything together. Einstein showed us why E equals mc squared. Energy and mass are two faces of the same thing. So a proton's weight, your weight, everything's weight isn't just matter. It's energy condensed, energy bound, energy made visible, which means the universe isn't heavy because of what it is. It's heavy because of how it moves, how it holds itself together, how it hums beneath everything we can see. And isn't that extraordinary? So here's something that always gets me. When we think about matter, the stuff we're made of, the stars, the air, everything, you'd expect the mass to come from, well, the matter itself, right? The particles, the substance. But it doesn't. Not really. More than 90% of it actually comes from energy, from the motion inside, from empty space that isn't really empty. That's strange, isn't it? Because the quarks, the little things inside protons and neutrons, they do have mass, yes, but not much. And for a long time, no one could explain why. Why them and not others? Photons, for example, light particles, they have no mass at all. Gluons, the carriers that hold quarks together, same thing, massless. Electrons and neutrinos, almost nothing. But then there's the W boson, a particle so heavy it outweighs an entire iron atom. How does that make sense? Why this incredible imbalance? That question haunted Peter Higgs back in the 1960 seconds. He kept thinking, there must be something we're missing, something invisible, something that gives mass to matter itself. And so he proposed an idea, bold and strange, that maybe in the beginning, just after the Big Bang, there were no massive particles at all. Everything was weightless. But then, within a tiny fraction of a second, a new kind of energy field appeared. It filled the universe everywhere, all at once. It didn't just exist, it changed everything it touched. This field, now called the Higgs field, gave particles mass, like a cosmic fog thick enough to slow them down, to make them heavy. And just like every field in physics, it had a messenger particle, a quantum whisperer, the Higgs boson. It would be the 17th piece of the Standard Model, one that explains how matter behaves, how it interacts, how it exists. But for decades, no one could find it. Half a century of searching, and still nothing. People began to wonder if it was even real. So in 1993, the British Minister for Science tried to make the search more relatable. He promised a bottle of champagne to anyone who could explain the Higgs field simply. Many tried, but it was David Miller from University College London who nailed it. He said, imagine a crowded party, people everywhere, chatting, moving. Now, if a regular person walks in, they can pass through easily. But if someone famous enters, everyone turns, they gather, they cluster, they slow the person down. The crowd is the Higgs field. The person, the particle, the more interaction, the more resistance, the more mass. And when rumors spread through the room about that person's arrival, the ripple through the crowd, that's the Higgs boson itself, the messenger of the field. It's not a perfect analogy, but it works, and it gave the world a way to picture something invisible. Still, finding that particle was like looking for a needle in a haystack when no one even knew what a needle looked like. Two giant machines took up the hunt, the Tevatron in the US and the Large Hadron Collider at CERN. They smashed particles together again and again, hoping the fragments would reveal a glimpse of the truth. For years, nothing certain. But then, in 2012, something shifted. The data lined up, the signals appeared, the Higgs boson was finally found. The theory was right, the field was real, and with it, one of the biggest mysteries of modern physics was solved. Because of that field, a trillionth of a second after the Big Bang, the universe changed. The perfect symmetry broke apart. The electroweak force split into two, forming the forces we know today, the electromagnetic and the weak nuclear. The Higgs field gave weight to everything that would ever exist. W and Z bosons became massive. Quarks and leptons gained their identities, while photons and gluons stayed massless, free. By the time the universe was a billionth of a second old, the quark era had begun. A sea of particles, hot and dense, filling the cosmos, ready to build everything, the stars, the planets, and eventually us. Out of that plasma, out of that chaos, came the architecture of everything we know, and somehow all of it, all the variety, all the complexity, traces back to that invisible field that gives weight to reality itself. You know, I've been thinking about stars lately. Some of them live fast, burn bright, and die young, gone in a few million years. Others take their time, glowing softly for trillions, almost eternal on our scale. Why such difference? What decides that pace? It's the same physics, the same matter, yet the outcomes are so wildly different. And then there are planets. So many kinds. Gas giants like Jupiter, all storms and pressure. Rocky worlds burnt dry by their suns, and then every once in a while, a planet covered in oceans and clouds, just the right temperature for life to begin. And life, well, that's another miracle entirely. On worlds like ours, it takes every form you can imagine, from tiny bacteria that breathe sulfur to creatures like us, who build telescopes and try to understand why we exist at all. When you think about it, the universe seems limitless in its creativity, infinite variety, infinite expression. But here's the strange part. Beneath that chaos, there are rules. Unchanging, unbreakable rules. No matter where you are, how far you go, the same constants whisper through everything. The laws of nature, fixed like the frame of a painting, defining what can exist and what cannot. And those constants, they're peculiar. Take the speed of light, for example. 299,792,458 meters per second. You think it's just a number, but no one knows why it's that number. Why not slower? Why not faster? It's as if the universe chose it and never explained itself. Or gravity, that invisible thread pulling everything together. Its strength is absurdly tiny. 6.6, 7 times 10 to the negative 11. Again, why? There's no reason it has to be that exact value. Yet if it weren't, nothing we know could hold together. And the list keeps going. There are constants linking energy to temperature, radiation to motion, light to magnetism, electricity to charge. Every one of them, precise, rigid, mysterious. Even the masses of the most fundamental particles, their weights, their charges, they're constant too, but seemingly arbitrary, as if the universe rolled dice and decided to keep the outcome. Richard Feynman once said that one number haunted him, the fine structure constant, this quiet ratio that describes how strongly particles feel electromagnetic forces. It's about 1 over 137, not 1, not 10, not 1,000, 137. He called it a magic number that comes to us with no understanding. Because if that number were different, even slightly, atoms wouldn't hold together, matter wouldn't exist, we wouldn't be here. If gravity were weaker, the universe would drift apart into nothing but hydrogen gas. If it were stronger, everything would collapse into black holes before life ever had a chance. So, coincidence? Design? Or something deeper? Some think it's luck. Some think it's intention. Others imagine that our universe isn't alone, that it's one among countless others, each with its own set of constants. Maybe most of them failed. Barren, empty, physics gone wrong. And only a few, like ours, had just the right mix to make galaxies and stars and life. Whatever the truth is, that fine-tuning began instantly. In the first fractions of a second after the Big Bang, the universe was already sculpting itself. By 1/1000th of a second, it was a storm of quarks and leptons and light, too hot for anything to bind. Then it cooled. Just a little 1/1,000,000th of a second later, it was still 1,000,000,000,000 degrees, but that was enough for gluons to catch quarks to form the first building blocks, protons and neutrons. You might think that's simple, but it's not. Each proton is a fragile collaboration of 2 up quarks and 1 down quark, all charged, all repelling each other, held together only by the strongest force we know. And even then, inside that proton, things never sit still. Most of its mass isn't from its parts at all, but from the energy of their motion, from the ceaseless dance of quantum fields. Sometimes a quark inside just turns into another kind called a charm quark, along with its antimatter twin. It happens in an instant, then they vanish again, like flickers in the dark. The proton survives. The universe continues. And we keep asking why these numbers, why these patterns, why this version of reality. Maybe we'll never know. Maybe that's the beauty of it. So here's something that still blows my mind every time I think about it. The proton, that tiny building block inside every atom, isn't really what we think it is. You'd imagine it's a neat little particle, right? Compact, solid, simple, but it's not even close. Inside, it's a blur, a storm really, made of quarks, the usual ones called valence quarks, but also gluons and even charm quarks that flicker in and out of existence. And that's the weird part, because those gluons and charms are what we call virtual particles. They're not exactly there, not in the way we think of things being there, but they still matter. They still make up almost everything. 99% of a proton, maybe more, is made from particles that don't really exist. How strange is that? But it works. It's the reason matter has mass at all. In the first 1,000,000th of a second after the Big Bang, these bizarre protons and neutrons started forming everywhere in that blazing plasma. They weren't stable yet, though. The universe was too hot, too dense. The weak force, one of the fundamental forces, kept flipping them back and forth. A proton could suddenly become a neutron, then back again, switching identities like it couldn't decide what it wanted to be. Only when the universe cooled, about 1 second old, did that dance begin to slow. We call that moment the freeze-out. That's when the hadrons, those early protons and neutrons, finally chose who they were going to be. And here's the beautiful thing. That choice, that balance, was shaped by the tiniest details in nature. The masses of the up and down quarks. Down quarks are a little heavier, just slightly. Because of that, neutrons, which have 2 downs, are a touch heavier than protons. It doesn't sound like much, but it changed everything. As the universe cooled, it became easier for neutrons to fall into protons than the other way around. That tiny tilt in the energy scale, just a whisper of imbalance, meant that protons began to outnumber neutrons, about 7 to 1. And that ratio, that little asymmetry, shaped the universe you live in. Protons make hydrogen, and hydrogen makes stars. Stars make helium, and from helium come all the heavier elements, carbon, oxygen, iron, everything we're made of. If it had gone differently, if neutrons had won, if the down quark had been just a bit lighter, the whole story would have changed. Hydrogen wouldn't have lasted. It would have decayed or fused too fast. Maybe we'd have had a few helium atoms, but helium doesn't like to play with others. It's stable, silent, unreactive, no chemistry, no biology, no us. Just a cold universe, dark and quiet, full of neutrons and nothing much else. So somehow the universe leaned toward protons, toward imbalance, toward life, and yet that wasn't the only imbalance written into the cosmos at that time. There's another bigger one. The mystery of antimatter. For every particle, there should have been an antiparticle. Perfect symmetry. But that's not what happened. Something tipped the scale. Matter won by the slightest margin, just enough to exist. And maybe somewhere out there, another civilization learned how to harness that difference. Imagine them far away, far ahead, turning that hidden symmetry into power. Not just fusion, not even fission, but pure annihilation. They build weapons, devices holding antimatter, trapped by electromagnetic fields, waiting. 1 gram of it could unleash the energy of 90 kilograms of nuclear fuel. Just 1 gram. So imagine what happens when something goes wrong. A misstep, a mistake, or maybe anger. The containment fails. Matter and antimatter meet. They vanish together in a flash brighter than a Sunday night turns today. Winds of fire sweep over continents. The world below burns. And all of it, every trace of life, gone in an instant. Maybe one day we'll look into the sky, see a star that flares just once, faint but real, and we'll know somewhere out there someone made the same discovery, and somewhere out there someone made the same mistake. The idea that something as small as a particle could destroy everything we know, antimatter, it sounds like science fiction, right? But it's real. It's here, around us, every day. The English physicist Paul Dirac was the one who first saw it coming back in 1928. He wasn't trying to imagine explosions or black holes. He was just doing math, combining Einstein's relativity with the new rules of quantum mechanics. But then something unexpected happened. His equations didn't just describe electrons, the negative ones we know so well. They also described something else, a mirror version, a positive twin, a new kind of particle, a positron, an anti-electron. And that's when the idea of antimatter was born. 4 years later, an American physicist named Carl Anderson actually found one, not in theory, but in a real machine, a simple cloud chamber used to catch cosmic rays. He saw the tracks curve the wrong way. That was it. Proof antimatter was real. And once you know it exists, you start to wonder, how far does it go? Does every particle have an opposite? So scientists went looking in the 1,950 seconds at the Bevatron accelerator in California. They found them the first anti-proton, the first anti-neutron. And then decades later, in 1995, they built the first anti-hydrogen atom. Imagine that. A mirror version of hydrogen itself. Since then, we've seen antimatter everywhere, from the violent hearts of supernovas to the jets of black holes. Even here on Earth, in something as ordinary as a banana, Radioactive potassium spits out a positron about once every 75 minutes. So antimatter isn't some far-off fantasy. It's part of the universe. Just a small part, though. Because here's the thing. The universe is almost entirely made of normal matter. For every quadrillion particles of matter, there's maybe one of antimatter. That imbalance is lucky for us. If the quantities were equal, everything would have vanished. Total annihilation. No stars, no planets, no us. But that raises the real question, doesn't it? Why the imbalance? How did matter win? At the beginning, matter and antimatter should have formed together, perfectly paired, each born from the same burst of energy. They should have met, collided, and destroyed each other almost instantly, leaving nothing but light. And yet, somehow, they didn't. Something tilted the balance. Maybe it happened between a millionth of a second and 2 minutes after the Big Bang. Somewhere in that sliver of time, 1 in a billion particles survived. One, and everything you see now comes from that small excess. But what caused it? Maybe it was symmetry breaking, the universe choosing a favorite. In the 1,950 seconds, physicist Chen-Sheng Wu showed that nature doesn't treat matter and antimatter exactly the same. The difference is tiny, but it's real. Still, not enough to explain everything. So scientists suspect there's more, maybe a missing piece, a vanished kind of particle that existed only in the first heartbeat of the universe. We call it the right-handed neutrino. We've never found one. Maybe it decayed away long ago, maybe into matter more than antimatter, tipping the scales forever. It's just an idea, but it fits. It could explain why we're here at all. Because if that decay had gone the other way, there would be no galaxies, no stars, no atoms, just radiation expanding into nothing. And it's strange, isn't it, that everything we are could depend on a preference, a flicker of asymmetry that decided to keep matter alive. When we look into the night sky, when we see galaxies curling and quasars blazing billions of light years away, we're really seeing the result of that ancient imbalance. A universe that almost didn't happen. These quasars, the brightest beacons in the cosmos, they're not just lighting up the darkness. They're also revealing something hidden, something delicate, a feature that stretches through deep space, like threads in a vast invisible web. It's called the Lyman Alpha Forest. Sounds poetic, right? But it's real. The constant speed of light through an expanding universe means distance is time. The farther we look, the older what we see. So when we look at distant quasars, we're seeing them as they were billions of years ago. Their light has been stretched, redshifted, pulled toward the red end of the spectrum by the expansion of space itself. But when astronomers examined that light more closely, something curious appeared. It wasn't just a smooth red glow. It had sharp dips, narrow valleys, carved into the spectrum. Why? What could carve light like that? At first it made no sense, but then came the realization each dip was the fingerprint of hydrogen, ancient and diffuse, floating in the vast emptiness between galaxies. Not trees, but clouds, thin clouds of hydrogen gas. And together they made this strange spectral forest. Every time light from a quasar passed through one of those clouds, a small piece was absorbed, a bite taken out of the spectrum. And when that light finally reached Earth, it carried with it a map of everything it had touched. Each dip in the forest was an invisible cloud, a signpost from billions of years ago. The deeper astronomers looked, the denser the forest became. At high redshifts, where the universe was young, those absorption lines crowded together so tightly, it was as if the cosmos itself was fogged with hydrogen. That's what the early universe was like. Not empty, not clear, but filled with low-density hydrogen, a kind of cosmic nursery waiting to give birth to stars and galaxies. All that hydrogen came from the very first moments after the Big Bang. By the time the universe was a single second old, it was already a place of unimaginable violence. 10 billion degrees hot, crowded with particles colliding, annihilating, reshaping, protons, neutrons, photons, all locked in a fierce equilibrium. And somehow, through the strange rules of physics, the balance of matter was set. The Higgs field had already done its work, giving mass to the particles that would one day make you and me. The four fundamental forces were already in play. The strong nuclear force holding protons together, electromagnetism binding atoms, the weak nuclear force guiding decay, and gravity bending space itself. Wild forces, chaotic but consistent, and from that chaos the universe began to cool and expand. For a long time, all of this was theory, a reconstruction of events no one could see. But now, at last, we're beginning to observe it directly. We can study the relics, the echoes left behind. Deep in Antarctica, there's a place where scientists drilled holes straight into the ice, 2.5 kilometers deep. They melted their way down, lowering instruments like strings of pearls into the dark. That's the Ice Cube Neutrino Observatory. You might think it's strange, a telescope that looks down instead of up, buried in solid ice instead of staring into the sky. But that's exactly what makes it perfect, because what it's looking for isn't light at all. It's searching for neutrinos, ghostly particles that almost never interact with anything. Every second, 100 trillion of them pass through your body, through the Earth itself, as if nothing were there. For decades, they were just an idea, a missing piece in an equation. In the 1,930 seconds, Wolfgang Pauli realized something was off in nuclear decay, a bit of energy missing, a piece unaccounted for. He imagined a particle so small, so shy, it could slip through matter untouched. And he was right. It took 20 years and a project called Poltergeist before physicists finally caught one. Since then, detectors have been built in the strangest places, at the bottom of lakes, in gold mines, under mountains, all to listen for whispers of the same ghost. So the light from quasars, the forest of hydrogen, the neutrinos beneath the ice, they're all pieces of the same story. A universe that hides nothing but never reveals everything at once. A cosmos that's still speaking quietly through the particles that never stop passing through us. You know, it's wild to think about how it all began. Cowan and Reines had this idea, and it sounded almost insane at the time. What if you could set off a 20 kiloton nuclear blast and then, just 50 meters away, build a detector big enough to catch the faintest whisper from the explosion? They called it El Monstro. It would have been 1,000 times larger than anything before it. Imagine that, an instrument so huge, so sensitive, that it could catch a flash of light born from a particle that almost never interacts with anything at all. But in the end, they couldn't make it work. Too dangerous, too complicated. So they turned to something quieter, something steadier, nuclear reactors, a controlled fire instead of an atomic storm. And in 1956, it happened. They did it. They found the ghost, the neutrino, the particle that had been hiding from physics for more than 20 years. You'd think something that small couldn't matter, but it changed everything. And since then, the hunt has only grown. Now we build accelerators, machines that hurl particles at near light speed, smashing them together to make new ones. And still, even now, we build monsters like the one beneath Lake Baikal, because sometimes only something enormous can see what's invisible. Why? Because neutrinos are everywhere. They're made in the hearts of stars, in nuclear fires, in explosions that tear galaxies apart. They come from the birth and death of matter itself. And if we can read them, really read them, they can tell us stories that light never could. Think about this. 168,000 years ago, a star in the Large Magellanic Cloud exploded. A supernova. Its debris flew outward almost at the speed of light, a storm of atoms and neutrinos sweeping through space. And then, in 1987, those ghosts arrived here. 11 of them. Just 11. But even that tiny handful told us something huge. It proved we could see the universe in more than light. We could listen to it, feel it. A new era of astronomy began, what we now call multi-messenger astronomy. gravitational waves, X-rays, radio waves, neutrinos, all working together, all telling different parts of the same story. And that story gets stranger because neutrinos go where light cannot. They slip through stars, through gas clouds, through whole planets. They barely notice matter at all. They only listen to two forces, gravity and the weak force. Everything else they ignore. That makes them perfect messengers for what light can never reach. The earliest times, the first second after the Big Bang, back then everything was chaos. The universe was so dense, so hot, that light couldn't move freely. For hundreds of thousands of years, it was trapped, bouncing endlessly off particles. The whole cosmos was opaque. But neutrinos, they were different. Less than a second after it all began, they were part of that hot, dense soup, colliding and scattering. Then, as the universe cooled to 10 billion degrees, something shifted. They slowed just enough to break free, the first to escape, the first travelers through the newborn universe. They left behind a trace, a kind of fossil made of motion and silence. We call it the cosmic neutrino background. And if we could find it, if we could detect those ancient ghosts, we'd be seeing the universe when it was only 1 second old. That's 380,000 years further back than light can ever show us. But here's the catch. These relics are even more elusive than the high-energy neutrinos we study today. Instead of billions in every cubic centimeter, there are maybe 300. To catch them directly, we'd need instruments 1 billion times more precise than anything we've built. Or maybe we could look for their fingerprints, the ripples they left when they first broke free. Like tiny sonic booms, frozen in the structure of the universe itself. The idea that such fragile, fleeting things could shape the cosmos, that's strange. But it's also, well, kind of beautiful, isn't it? Some parts of space ended up just a little warmer, others a little cooler, because something disturbed the balance right after the beginning. And over the next 13.8 billion years, space stretched, and those tiny ripples stretched with it. What started as microscopic wrinkles became the vast pattern of galaxies we see now. And here's the strange part. If we could decode that pattern, if we could read the way galaxies are scattered across the sky, we might be listening to the echo of a universe only 1 second old. 1 second. Can you imagine that? But that's not the only mystery left behind from that ancient instant. There's this thing, TON 618. But it's real. It's out there, about 18 billion light years away, burning 140 trillion times brighter than the Sunday, one of the brightest objects we've ever found. You'd think it's a massive cluster or something. But no, it's a single galaxy with a black hole so huge it outshines everything around it. 11 billion years old. At its heart sits a hypermassive black hole, 66 billion times the mass of the Sunday. Think about that. 66 billion suns crushed into 1 point. It's 15,000 times heavier than Sagittarius A star, the black hole, at the center of our own galaxy. In fact, it outweighs every single star in the Milky Way combined. The scale of it is ridiculous. The thing is so vast that its diameter is 40 times the orbit of Neptune. That's the orbit, not the planet. And matter doesn't just fall into it slowly. It's racing inward at over 10,000 kilometers per second. That speed creates friction, pressure, heat. The gas around it glows white hot, shining brighter than entire galaxies, even though at the center there's only darkness, a hole that no light escapes. But no, TON 618 isn't alone. There are others. Supermassive black holes, hundreds of thousands or millions of times the mass of the sun, sitting quietly in the centers of galaxies, shaping how those galaxies form and grow. They're everywhere. But there's a problem, a timing problem. Because when astronomers look back far enough, they find these giants existing only a few million years after the Big Bang. That's too soon. Our models say stars need time, lots of time, to live, die, collapse, feed these monsters. Yet somehow, in less than 1 billion years, some black holes already reached 1 billion solar masses. How, according to the math, that shouldn't be possible. Maybe we're missing something. Maybe there's another way. And there is a theory, one that goes back to 1971, when Stephen Hawking asked a question that still echoes today. What if some black holes were never born from stars at all? What if they came straight from the beginning, from density fluctuations in the newborn universe itself? He called them primordial black holes. Picture it, the early universe, a seething soup of energy, radiation, matter, all tangled together, and within that chaos, tiny irregularities, some regions denser than others. Gravity would have pulled on those lumps, crushing them inward before the universe had a chance to cool, forming black holes in the blink of an eye. But here's the catch. It could only happen in a narrow window, about 1 second long, just after the Big Bang, before expansion and cooling spread everything too thin for gravity to work its magic. 1 second to create the seeds of the darkest giants we see today. 1 second that may have shaped everything that came after. So imagine this. The universe, right after it began, was wild. Everything expanding, heating, cooling, all in seconds. And somewhere in that chaos, maybe, just maybe, something strange happened. Some regions got denser than others, dense enough to collapse. And what happens when matter collapses that much? A black hole, but not a normal one, not born from dying stars. These would be the first. The primordial black holes formed almost instantly after the beginning. Could these ancient black holes still be out there? Could they be the missing seeds for the gigantic ones we see now, the ones too massive to make sense any other way? The math seems to say yes, or at least it doesn't say no. It fits what we know about the early universe, about how matter behaved, but we don't know when exactly they formed. Was it a billionth of a second after the bang? A whole second? It matters, because the later they formed, the bigger they'd be. And that size range, it's absurd. Some could weigh less than a grain of dust, 100,000th the mass of a paperclip. Others could be monsters, 100,000 times heavier than the Sunday. One way, oddly enough, is to look for their destruction. Stephen Hawking had this idea back in the 1970 seconds. He said black holes aren't completely black. They leak, they lose energy through something we now call Hawking radiation. And the smaller they are, the faster they lose it. It's like they burn themselves out. A tiny black hole would evaporate in a flash, an explosion as bright as 1 million hydrogen bombs. If any black hole had less than 100 billion kilograms of mass, it should have died by now, vanished, but maybe it left a trace. So we built instruments to look. The Fermi Gamma Ray Telescope scans the sky for those faint cosmic aftershocks, those final death screams. So far, nothing. At least nothing definite. Other methods try to catch them indirectly, like when a black hole passes in front of a star and bends its light just slightly. A flicker, a magnification called microlensing, or by looking for stars torn apart in invisible gravitational traps. Each test narrows the window, rules out certain sizes, certain ages. The mystery shrinks, but it's still alive. And no one's giving up. The next generation of telescopes is already reaching farther. The James Webb Space Telescope, it's peering into the first galaxies, maybe even the places where these primordial black holes were born. And then there's LISA, the Laser Interferometer Space Antenna. It will float in space, listening for gravitational waves, faint ripples from collisions, or ancient black holes still drifting since the dawn of time, since the universe was barely a second old. It's strange to think that what we call primordial might still be moving around us. But that's not all. On Earth, we're doing something just as extraordinary. On December 5th, 2022, at the National Ignition Facility in California, scientists did what stars do naturally. They made fusion, not bombs, not weapons, but real controlled fusion. They fired 192 lasers into a tiny gold capsule, smaller than your thumb. Inside was a peppercorn-sized fuel pellet, hydrogen isotopes called deuterium and tritium. When the lasers hit, they heated the chamber to 3 million degrees Celsius, hotter than the surface of the Sunday X-rays, blasted out, crushed the fuel inward at 400 kilometers per second. The pressure reached 100 billion times Earth's atmosphere. And then it happened, the atoms fused, hydrogen became helium, energy burst free. In that instant, more energy came out than went in. 2.05 megajoules in, 3.15 out. For the first time in human history, a fusion reaction that produced a net gain. The result? Enough to boil 20 kettles of water, but that's not the point. The point is what it means. After 70 years of trying, we finally matched the stars. We recreated the process that's been running in the universe for billions of years. And yet, the cosmos figured it out in its first minute. That's humbling, isn't it? We've always been obsessed with transformation, with turning one thing into another. Flowers from air lead into gold, dreams into reality. But the universe, it's been doing that from the start. In those early seconds, matter itself was changing identities, particles swapping roles, forces shaping what could exist, and it still happens now. Radioactive decay, fission, a carbon atom becoming nitrogen, uranium splitting into smaller fragments. It's all part of the same story. Change, decay, renewal, elements transforming quietly, predictably, even here, even now. You're surrounded by it. The same dance that forged the stars is still at work in your body, in the earth, in every atom that ever lived. So, fusion. The other kind of nuclear transformation, the one that builds, not breaks. Atoms joining together, merging into something heavier. But it's not simple. It's hard. Harder than almost anything we try to do. Because every atom, every nucleus, carries its own identity. That identity comes from the number of protons and neutrons packed inside. Hydrogen, for example. Just one proton. That's it. One tiny positive charge, and already a whole element is born. But it has varieties, isotopes, some heavier, some lighter. Protium has no neutrons at all. Deuterium adds 1. Tritium adds 2. Same family, same element, different weights. And when you add one more proton, everything changes. 2 protons make helium. Helium-3 if there's 1 neutron. Helium-4 if there are 2. Stable, balanced, glowing. But here's the thing. Those protons, they don't want to be together. They repel, they scream, stay away because of the electromagnetic force. Like charges push apart. And yet, there's another force waiting, stronger, deeper, the strong nuclear force. It's what binds quarks into protons, protons into nuclei, matter into everything you see, but it only works when things are unimaginably close. So how do you make 2 protons, both positive, come close enough to touch? You crush them. You heat them. You create conditions like the heart of a star. Temperatures of millions, even billions of degrees. Only then does the strong force win. Only then does fusion happen. Hydrogen becomes helium, mass becomes energy, light, life. But to go further, to build heavier elements, you need something even greater. You need chaos. Supernovae, colliding stars, the kind of violence that rips atoms apart just to remake them again. That's where gold, uranium, all the heavy metals are born. Not in peace, but in explosion. And we've tried to copy that here in labs, in reactors, tiny stars trapped in metal spheres. We understand the math, the reactions, the way nuclei dance in stellar furnaces. We've even seen it start to happen in failed stars, brown dwarfs. Those in-between worlds, not quite planets, not quite stars, too small to fuse protium, the lightest hydrogen, but just heavy enough to fuse deuterium, the heavier kind. They glow faintly, powered by that fragile temporary fire. But even that doesn't tell us where deuterium and helium came from in the first place. Because to understand that, we have to go back. Way back. Before stars, before light, before time had meaning, back to the first minute of the universe. The temperature then was beyond imagination, about 10 trillion degrees. It had just dropped enough for quarks to combine into protons and neutrons, the building blocks of everything that would ever exist. But no stars yet, no galaxies, just a seething plasma expanding into darkness. Then came a long silence, 100 million years before the first stars began to shine, before fusion returned. So where did those first atomic nuclei come from? That question haunted scientists for decades until, in 1948, a young physicist named Ralph Alpher, working with George Gamow, proposed an answer. Big Bang nucleosynthesis. The birth of the first elements forged not in stars but in the universe's own beginning. It was a brilliant idea, one that changed everything. Their paper became famous not just for its insight but for its title, Alpha, Beta, Gamow. Alpha, Beta, Gamma, a cosmic joke that became legend. But beneath the humor lay something profound. It showed how the newborn universe, burning hot and dense, could turn simple hydrogen into helium through a fragile bridge of deuterium. Protium, the simplest hydrogen, appeared first. A single proton, nothing more. As soon as quarks bound together, it existed. But it took time for real atoms to form, for electrons to settle into orbit. Around 10 seconds after the Big Bang, it was cool enough for deuterium to appear. One proton, one neutron. But the universe was still so hot, so full of radiation, that these new nuclei couldn't survive for long. Every photon that struck them could tear them apart. That's what physicists call the deuterium bottleneck. The moment when creation itself was stuck, waiting for the universe to cool just a little more. Because until that barrier broke, fusion couldn't continue. The universe was ready to build, but it had to wait. And that waiting, that delicate pause, is the reason we exist at all. So around 300 seconds after the beginning, the universe cools just enough for something fragile to survive. Deuterium, a proton and a neutron finally able to hold each other without being torn apart by heat. It does not sound like much, right? But that little stability, that tiny pause in chaos, changes everything. Because now deuterium can fuse. It can join with other protons under the crushing weight of the cosmos itself. And what comes out of that is something new, something stable, helium-3. The first real element the universe ever made. From there, it keeps going. Helium-4 forms next, 2 protons, 2 neutrons, the perfect symmetry. The most stable nucleus known, harder to break than anything else. And because of that perfection, almost all the free protons at that time get locked into helium. They go no further. The math fits. The energy, the balance between protons and neutrons, all of it predicts a universe made of roughly 25% helium by mass. And when we look today, more than 13 billion years later, that is exactly what we see. Still about 23% helium. The universe has changed in every other way, but that ratio remains. It is a fingerprint from the beginning, a quiet confirmation of Alpher's theory. And it is another example of how precisely tuned those first moments were. Because if the ratio had been off, even a little, everything would be different. Too many neutrons, too little hydrogen, and the universe would have filled with unreactive helium. No chemistry, no stars, no galaxies, no us. And if matter had been packed just a bit tighter back then, more helium would have formed, choking out the future before it even began. But that did not happen. Somehow, the conditions were just right. Even as the hadrons settled into their helium nuclei, the universe still glowed with enough energy to keep fusing, still racing to see how many new elements it could make before the temperature dropped too low. And after about 1200 seconds, 20 minutes since it all began, the great nuclear furnace sputtered and went dark. Still unimaginably hot, but not hot enough for any more nuclei to form. Only 4 elements now existed: hydrogen, helium, lithium, and beryllium. And beryllium, fragile as it was, could not last. So really, only the first 3 survived long enough to seed the first stars to become the fuel for the 98 other elements we know today. At that moment, for every helium nucleus, there were 12 of hydrogen, and for every particle of matter, 1 billion photons of light. Just energy and possibility. From those simple beginnings, everything else would come. Even the deuterium and tritium that scientists fused in California in 2022 were first born in that fire, in that newborn universe. 13.8 billion years ago. Life itself is the echo of that chemistry, a miracle of carbon and oxygen and hydrogen formed from that same cosmic recipe. And as far as we can tell, that miracle has only happened once, on a small wet rock circling an average yellow star on the edge of a spiral arm of the Milky Way. But how did life begin? We have fossils that go back 3 billion years, yet the moment of the first spark, the true genesis, is lost. We know life is built from organic molecules made of carbon, oxygen, and hydrogen. We know that every living thing shares the same code, DNA and RNA, built from nucleobases, cytosine, guanine, adenine, thymine, and uracil. A shared alphabet that writes everything from a leaf to a flipper to a thought. But where did those molecules come from? Did Earth make them in its warm, young oceans through chemistry alone? Or did they arrive from beyond, born among the stars, carried across space before ever touching the sea? The truth might be somewhere in between. But either way, it all began in that first light in those 20 minutes when the universe learned how to build. You know, it's strange how the universe keeps whispering clues about life, not just here, but far beyond. We used to think the cosmos was silent, empty, but it isn't. In 1969, astronomers in West Virginia pointed a radio telescope toward the void and caught something impossible. A vibration. Not random noise, but the spectral fingerprint of formaldehyde drifting between the stars. Carbon, hydrogen, oxygen, all floating free, building blocks of life, suspended in the cold. And that was only the beginning. Since then, scientists have identified more than 250 complex organic molecules out there. Aldehydes, alcohols, acids, amines, each one a quiet rehearsal for biology. So you start to wonder, right, how can chemistry be so alive in places so lifeless? And then you remember, maybe it has always been this way. Maybe the universe itself is a chemist. The evidence doesn't stop in space either. In 1864, in a small town in France, a meteorite fell, breaking apart into 20 pieces. People saw it streak across the sky, glowing, and when scientists examined it, they found something strange. It looked like peat, like the dark matter of Earth's own swamps. Could it be biological? No structures, no cells, nothing alive, so the idea faded. But nearly a century later, when new instruments looked again, something extraordinary appeared. Hidden within the stone were nucleobases, adenine and guanine, the same molecules that form the rungs of DNA and RNA, the code of life itself. And that wasn't all. Other meteorites from Australia, Kentucky, Canada carried the rest. Cytosine, thymine, uracil, even a few that Earth life doesn't use at all. The cosmos doesn't need a spark. It already knows how to build. Spark, even before stars, before planets, it was learning. Less than 100,000 years after the Big Bang, when the universe was still young, dense, and blazing, something remarkable was happening. The great fire of creation had cooled just enough for atoms to form. It was still too hot for electrons to settle, the air thicker than anything we could breathe, but already the first chemistry had begun. Helium and hydrogen, the simplest pair, started their dance. And from that dance came the first molecule ever, helium hydride. We made it in labs in 1925, unstable, fragile, gone in an instant. But could it have filled the early universe? In 1978, a man named John Black thought so. He imagined clouds of gas around dying stars, red giants casting off their layers, helium ions hungry for electrons. What would they steal from? Hydrogen. The moment they touched, helium hydride would be born, a tiny spark of chemistry in the void. For decades, no one could find it. Telescopes searched and failed. Too faint, too fleeting, until 2019. That year, a telescope did something different. Not on a mountaintop, not in orbit, but bolted into the back of a Boeing 747, flying higher than 43,000 feet. A flying observatory. They called it SOFIA. And at that height, above almost all the water vapor, the instruments could finally see the wavelengths the Earth normally hides. And there, at last, they found it. This signature of helium hydride, the first bond in the universe. Proof that chemistry began almost as soon as time itself. So when you look up, remember the cosmos doesn't just hold stars. It holds recipes, experiments, tiny sparks that began long before life and are still unfolding now. So there's this telescope, right? And it's connected to something called the GREET receiver, which is kind of perfect because that's exactly what it is. It listens in the far infrared, way out beyond what our eyes can see. And with that sensitivity, it finally caught something that for decades had only been a theory, a ghost of a signal. The first molecule in the universe, helium hydride. You can imagine the excitement because this was not just any detection. It came from 3 days of listening to a planetary nebula named NGC 7027, about 3,000 light years away in the direction of Cygnus, one of the brightest, hottest nebula in the sky. Why there? Because that's where conditions are wild enough, energetic enough for helium hydride to exist. And that's exactly what John Black had predicted 40 years ago. It's strange, isn't it, that something so old, so fundamental could hide from us for so long. But now we've seen it, and that means something bigger. Because inside that nebula, the conditions mirror what the universe itself was like just tens of thousands of years after the Big Bang. So even though this helium hydride isn't primordial, its presence tells us what could have happened back then, how chemistry began in the first place. You see, right after the Big Bang, space was chaos. The universe was full of energy, too hot for atoms to hold together. There were just nuclei, protons, helium, deuterium flying freely. Then, slowly, the heat began to fade down to about 4,000 Kelvin. That's when things started to change. At that temperature, the ions began to calm down, to combine in order, step by step, following the rules of their ionization potential. And helium, well, helium has always been the most noble of gases. The least reactive, the hardest to strip apart. You need an enormous amount of energy to pull one of its electrons away. It just doesn't like to share. But back then, when everything was charged, when everything was an ion, that very stubbornness made helium the first to grab an electron and keep it and keep it forming the first neutral atom in existence. But even that stability didn't last. It was still too hot for protons to capture electrons on their own. So the protons turned to helium, to those balanced electrons, looking for a way to share, and eventually, under that pressure, helium gave in. The first chemical bond formed. Helium hydride was born. Briefly, yes, but enough to open a door. Because once that happened, other bonds could follow, other molecules could form. That was the beginning of space chemistry around 100,000 years after the Big Bang. Today we call that field astrochemistry, and it's thriving. We can predict what molecules exist out there, how they form, where they might hide. Many are familiar, like water and ammonia. Others are far stranger, like dihydrogen monochloride cations or hydroperoxyl, some we've never even found yet, but they all trace their ancestry back to that first fragile molecule, that helium hydride that appeared and vanished and began everything. And here's the humbling part. You think you understand the world around you, right? You see, you hear, you touch, you taste. You think that's reality. But it's not. There's so much more happening all the time, just beyond those senses. Take light. We see in color, yes, but that's only a sliver of the electromagnetic ocean we're living in. There are waves shorter than any color, gamma rays, X-rays, streaming through us right now. From food, from walls, from our own bodies. The sun bathes us in radiation, and only a tiny part of it is visible. About 10% is ultraviolet, invisible but strong enough to burn skin, to change DNA. Half of it is infrared, light too long for our eyes, but warm to the touch. Every warm object glows with that invisible light, including you. You shine constantly, just not where you can see it. And lower still, there's more. Infrared used in remotes, in motion sensors, signals flickering all around, passing through walls, through us, unseen but real. So the next time you look around and think you know what's there, remember this. What you see is only a fraction, a whisper of the real world. The rest is there too, hidden, waiting, glowing quietly in the dark. Everything around you right now, every message you send, every map you check, every song you stream, it all travels through invisible waves. Bluetooth, Wi-Fi, mobile signals, GPS, all of them whispering across the air on microwave frequencies. Microwaves, yes, the same kind of radiation that heats your dinner, just much weaker. And while those are buzzing around us constantly, there's something else, the old ones. The radio waves, those long, gentle ripples of the electromagnetic spectrum that carry voices and songs and news, they've been washing over us for a century, and they never stop. All of these waves, all that low energy radiation, it's everywhere, filling every corner of space, all the time. And if we could see it, really see it, the world would vanish behind a blinding fog of invisible color. We live in it, but we don't notice. We sense almost nothing. For all our intelligence, we're blind to 99% of what's happening in the universe. Maybe that's good. Maybe that's what keeps us sane. Because if we could sense it all, every pulse, every flicker, every vibration, our minds would drown. The quiet night sky would explode into motion, a storm of light and sound. Imagine it. Sharp points of energy where stars sing, a faint hum from gravitational waves rippling through space, and behind it all, an ancient afterglow, the fading light from the birth of everything. That glow, it's real. It's still there, but it wasn't always visible. In the first few 100,000 years of the universe, light couldn't travel freely. The cosmos was full of photons, yes, but none could escape. It was like being trapped inside a glowing fog. You'd think light should shine, right? But it didn't. The newborn universe was so dense, so energetic, that every photon crashed into particles before it could move an inch. It's strange to think that for all that brightness, it was completely opaque. Only when things cooled did the fog begin to clear. As energy stretched and thinned, the wild sea of particles slowed enough for something miraculous to happen. Matter began to form. Not just particles, but atoms, the first stable ones. Think about that. For 380,000 years, electrons were too energetic to settle down. The electromagnetic force kept trying to pull them in, but space was too hot, too wild. Then finally, when the temperature dropped to about 3,000 Kelvin, electrons joined protons and neutrons, locked together by attraction. The first true atoms were born, and when that happened, everything changed. Suddenly, photons could move freely. They burst out, streaming across the universe in straight lines, the first real light. What was once opaque became transparent. What was plasma became gas. The universe went from chaos to clarity in a single cosmic moment. And that ancient light, the one that finally escaped, it's still out there. We call it the cosmic microwave background. It's the oldest thing you can see. But the story doesn't stop there, because billions of years later, in the 1,960 seconds, two scientists, Arno Penzias and Robert Wilson, were just trying to do something simple, tune a radio antenna in New Jersey. They weren't looking for the beginning of time, they just wanted to clean up the noise. But that noise, that faint hiss they couldn't get rid of, turned out to be the whisper of the universe itself, the echo of creation. And that's how one of the greatest discoveries in science began, not with a plan, not with intention, but with curiosity, with two people listening carefully enough to hear the universe speaking in the background. They started listening, and right away something felt off. A low hiss, steady, soft, but everywhere. It wasn't from one place. It was from every direction, like the whole sky was whispering at once. That didn't make sense, so they thought it had to be a mistake, something wrong with the instrument. And then they found them pigeons, two of them roosting inside the great horn of the antenna. And their droppings, a thin layer of what they called a white dielectric material, could that be it? Could that faint warmth, that residue, be making the noise? They cleaned it, tried to rehome the birds, failed, tried again. Eventually they cleared the horn completely, both pigeons and the mess. But the hiss stayed. It would not go away. Penzias and Wilson had run out of suspects. Every error was gone, every fault removed, and yet the sound was still there. They called a man at Princeton, Robert Dick, to ask. And Dick, well, he knew exactly what they had stumbled upon. He had been working on a theory, a vision of the early universe, when atoms first formed, when light broke free for the first time. He believed that after the Big Bang, there was a moment called recombination, when the cosmos cooled just enough for electrons to settle into atoms, and the universe turned transparent. That first light, bright yellow-orange, should still be here, he said, but stretched, faded by billions of years of expansion, until it became a faint microwave glow. That was what Penzias and Wilson were hearing. They had found it without even knowing what it was. And so, by accident, they discovered the echo of creation itself. A decade later, it was the Bell Labs pair who received the Nobel Prize, not Dick. But it hardly mattered, because what they had found changed everything. That faint signal, just 2.7 degrees above absolute zero, was proof that the universe really did begin hot and dense, the oldest light still shining. It comes from a time 380,000 years after the beginning, but it carries the story of everything that followed, the earliest snapshot we have of a young, energetic universe still forming itself. Later missions studied that glow in detail, satellites like COBE, WMAP, and Planck. They found tiny variations, patches slightly warmer or cooler by a few hundred thousandths of a degree. And those tiny ripples, those small differences, turned out to be the seeds of everything. The places where galaxies would grow, where gravity gathered more matter, where the first stars would burn. All of it began as a whisper in that light. And when they looked even closer, they saw patterns, not random exactly, not pure chaos. There were ripples, echoes, frozen waves from a time when the universe was still a dense plasma, a sound-filled ocean. Back then, gravity pulled matter inward, but photons trapped in that hot soup pushed back, outward, rebelling against the crush. The result was waves, expanding spheres of pressure that spread through space like raindrops on a cosmic pond. And now, billions of years later, those ancient vibrations still shape the universe. The sound of creation stretched into silence, still echoing faintly in the sky. The early universe could sing, not with voices, of course, but with pressure, with ripples of density moving through the hot plasma of creation. These waves, these compressions and rarefactions, they were sound, real sound. Cosmologists call them baryonic acoustic oscillations, but they did not last. Something happened, the universe cooled. It reached a temperature of about 3,000 Kelvin. Electrons began to settle into atoms, light broke free, and suddenly those waves stopped. The photons that had been pushing matter outward escaped, racing away across space, leaving the ripples frozen in place. That sound itself could stop mid-note and remain imprinted across the cosmos. 13.5 billion years later, those frozen ripples are still visible, stretched and enlarged by the expansion of everything, written into the vast web of galaxies and clusters. When cosmologists look out into that deep structure, they can still trace the rhythm of those first vibrations. Each ring of matter, now about 150 megaparsecs wide, nearly 500 million light-years, a standard ruler for measuring the growth of the universe. It is astonishing that something so ancient, so silent now, can still tell us how fast space is stretching. With it, astronomers can map the unfolding of time itself, not just how the universe was, but how it will be. The first light, the afterglow of that recombination, has dimmed, stretched thin, but it is not gone. It will take trillions of years before it fades completely. Plenty of time for future minds to listen again, to read the echo of those primordial waves, and then, in the darkness, new light begins. A spark, then another, a chain reaction of stars flaring to life. A cluster forms, gathering, glowing, until its own gravity makes it spin. Faster and faster until it flattens into a disk, turning once every 250 million years. A young galaxy, a spiral, sweeping through intergalactic space, collecting others as it goes. Smaller clusters fall into it. Sometimes they collide head-on, merging, igniting bursts of star formation. 10 billion years ago, this was our Milky Way in its youth. A churning spiral alive with light. Inside its arms, massive stars were born, burned fiercely, died spectacularly, and their ashes seeded the galaxy with heavy elements, the raw material for new generations of suns, and, for the first time, planets. Far from the center, about 25,000 light years out, a modest yellow star flickered into being 4.5 billion years ago. Around it, a disk of dust and gas swirled and clumped. Dust became pebbles, pebbles became boulders, boulders became worlds. Those worlds fought for position, colliding, shattering, reforming, until the system settled into its graceful clockwork. On the third planet from that star, heat gave way to water. Oceans condensed, rocks broke, and were born again. And somewhere in that restless sea, chemistry found a spark. Life, simple at first, then growing, branching, diversifying, turning matter into meaning. The sea filled, the land stirred, the sky breathed. And then, after billions of years, something new opened its eyes and asked why. A mind, a being aware of its own origins, looking back at the stars that built it. We can trace the sequence now. We know the steps: the galaxy, the sun, the earth, life, us. But even with all our equations and instruments, there are still gaps, still mysteries left unsolved. And maybe that's the point. The story of creation is not finished. It is still unfolding, one question at a time. How did it all begin, really? How did that lumpy soup of atoms floating in the young universe, just a few 100,000 years after the Big Bang, become all of this? You, me, stars, galaxies, everything. Was it inevitable, or could it have turned out differently? You'd think with the same matter, the same energy, the same starting rules, we'd always end up here. But no. When scientists run the math, when they simulate what happens after atomic recombination, the universe they get isn't quite ours. It looks familiar but off, like a dream version. Fewer galaxies, fewer stars being born, planets taking longer to form. In some of those simulations, there's no life at all. Nothing looking back. Something invisible, something we can't see but somehow must be there. Because around 380,000 years after the Big Bang, something changed. Light, trapped for so long in a fog of matter, finally escaped. Photons could travel freely, spreading out through the expanding universe, but as they moved, they lost energy. The universe became transparent, yes, but also dark. The wild brightness of creation had faded. Fusion hadn't started yet. Stars didn't exist. The cosmos was quiet, almost still. These were the Dark Ages, not because nothing was happening, but because we couldn't see what was. And yet something was moving in that darkness, something shaping what would come next. Dark matter. What is it? We still don't know. But we think it was there then, stepping forward when everything else went dim. The idea goes back to 1933, when Fritz Zwicky, a Swiss astronomer, looked at the Coma cluster, 300 million light years away, and saw something strange. The galaxies were moving too fast. By all logic, the cluster should have flown apart. So he did the math. The visible mass, the stars he could count, wasn't enough. Not even close. 10 times too little, something unseen. He called it Dunkel Materie, dark matter. And for decades, that was it. A mystery, a whisper in the data, until the 1,970 seconds, when Vera Rubin turned her telescope toward the Andromeda galaxy and saw the same impossible thing. Stars at the edges moving as fast as those near the center. It shouldn't happen. The outer ones should crawl, not race. But they didn't. They moved in defiance of everything we thought we knew. Most of the galaxy's mass was invisible. Not stars, not gas, something else entirely, something wrapped around it like a vast halo. Rubin calculated that the visible part made up only about 15% of the total. The rest was dark, and the deeper astronomers looked, the more they found the same pattern everywhere. Galaxies floating inside enormous cocoons of unseen matter. Even ours. The Milky Way's halo may be 15 times larger than the glowing disk of stars we see. And that means what we call normal matter. Everything that shines, everything we touch, is just a trace. Dark matter outweighs it 6 to 1. 6 to 1, that's the riddle. Maybe it's normal stuff, just hidden. Things like black holes, dead stars, brown dwarfs, too faint to see. Astronomers call them machos, massive compact halo objects. But the better our instruments get, the less likely that seems. We'd have seen them by now. So maybe it's something else. Maybe most of the universe is built from particles we've never touched, never detected. Weakly interacting massive particles. WIMPs. They pass through us, through everything. Ghosts of matter that sculpt the cosmos but leave no mark. The most important ingredient in the universe might be the one we can't see, can't feel, can't prove, only infer from the way galaxies move. It's there, everywhere, holding the universe together, quietly, invisibly, as if creation itself needed a secret scaffold just to stand. You know, this part of physics, it gets strange. These particles, if they exist, they would be something new entirely, outside the standard model, beyond everything we've tested so far. And we haven't found them yet, not a single one. But the math, the models, they keep hinting that they should be there. They wouldn't talk to normal matter the way other particles do. No electric charge, no strong interaction, no weak interaction, only gravity. Just gravity. And still, somehow, they would weigh enough or be so numerous that together they make up the missing mass of the universe, that hidden 85%. So what are they? WIMPs, maybe. Weakly interacting massive particles. It's a funny name, right? Sounds small, but if they're real, they're everywhere. The search is happening right now, deep underground, in accelerators, in the vast silence of the cosmos. But it's slow work, because how do you find something that barely leaves a trace? Maybe it will take years, maybe decades, or maybe we're looking the wrong way. Because whether dark matter is a WIMP or a Mako or something else entirely, it seems it's been here since the beginning, hiding in the shadow of ordinary matter from the first fractions of a second after the Big Bang. And back then, about 1 million years later, in the so-called cosmic dark ages, it started shaping everything. That's when the universe began to form its structure. The cosmic microwave background shows us that matter and energy weren't spread evenly. There were tiny ripples, tiny imperfections. And dark matter, it followed those ripples. Gravity pulled it together faster and tighter than ordinary matter could. Dark matter became the scaffolding, the invisible web, and normal matter began to gather where it had already clumped. The first filaments, the first clusters, the first galaxies, all born out of invisible patterns. From that point, the path of the universe was set. Everything since then, every star, every world, every breath, grew out of that early architecture. In the first million years, the stage was built for billions more. The universe cooled. Physics took shape. The four forces settled, each with its own role. Matter stabilized. Chemistry began. The story of stars and galaxies and eventually life was written into those first equations. But something changed later. 5 or 6 billion years ago, not long before our own solar system formed, the universe started behaving differently. The expansion, the one that had been slowing down, began to speed up. That shouldn't have happened. Gravity should have been pulling things together. So what was pushing them apart? Astronomers first noticed it in the late 1990 seconds, studying distant supernovae, those exploding stars that act like cosmic lighthouses. They shine with predictable brightness, so they tell us how far away they are. But something was off. The light from those explosions was stretched more than expected, more redshifted, as if the galaxies were moving away faster than the models allowed. And not just faster, accelerating. The acceleration itself was accelerating. The best answer we have is something called dark energy, a force that makes the universe expand faster and faster. And for the last 5 billion years, we've been living in that era, a dark energy-dominated universe. Einstein once imagined something similar, the cosmological constant, a kind of energy built into the vacuum of space itself, empty space that isn't empty. As the universe expands, there's more space, and therefore more of that energy driving even more expansion. He dropped the idea later, called it his biggest mistake, but maybe it wasn't a mistake at all. Maybe he was right for the wrong reason. The trouble is, we still don't know why it's there. Why should nothing have energy? Why should emptiness push? Some physicists think the answer might lie in the quantum world. In vacuum energy, in those fleeting virtual particles that appear and vanish everywhere, all the time, they create pressure, a push outward, tiny but constant. Could that be it? Could those invisible fluctuations be the breath that inflates the cosmos? It fits, almost. But when we do the math, it doesn't quite work. The numbers come out far too large, off by absurd amounts. So maybe the truth is something else, something we haven't imagined yet. Maybe dark energy, like dark matter, is the universe's way of reminding us that we're still guessing. That even now, after all the light and all the time, we've only begun to understand what nothing really is. So some cosmologists are starting to wonder, what if the answer is not a constant at all? What if it changes? What if there is a new kind of energy field out there, something alive in a way, shifting, breathing through time? They call it quintessence, a field that can be both attractive and repulsive, that can pull and push depending on when and where it is. You cannot grab it, you cannot trap it, you can only look for the traces it might leave behind in the way galaxies drift apart. But so far, nothing clear, no experiment that can pin it down, no observation that can prove it is real. And so we wait, watching the universe stretch around us, time passing, space itself expanding, and still that question lingers. What is driving it? Whatever it is, it fills almost everything. About 68% of the cosmos is dark energy, 27% is dark matter, and less than 5% is the ordinary stuff, the atoms, the light, the stars, the things we can touch. Just 5%. Can you believe that? Everything we have ever known comes from that thin sliver of existence. The rest, invisible, untouchable, but shaping everything. And from those ingredients, the universe has grown, evolved, changed for nearly 13.8 billion years. All of it unfolding according to the same rules, the same constants set in those first impossible moments in the first 10 tridecillionths of a second after the Big Bang. Imagine that the laws of everything written before there was even light. If you are still here, maybe still half awake, leave a small wish for someone else below. A quiet good night. A tiny light in the dark. And if you want, you can help us grow by liking or subscribing so more dreamers find their way here. But if your eyes are already heavy, do not worry. Just drift. Let go. The galaxy will keep turning without you. Gently, endlessly, as it always has.